We're on Unit 7, Chemical Kinetics and Equilibrium. These are the notes for it. Please go ahead and press pause and fill in the blanks for all the key terms that are on your guided notes, and read this paragraph, the starting paragraph, once, twice, and 3 times over to make sure that you understand the main ideas for this unit. In studying kinetics, we're looking at the rate, the average rate. And we're going to find out that the average rate is really the slope, the chord that links the 2 time points that you're going to be measuring. And the average rate could be positive or negative depending on if the substance is decreasing or increasing over time. And to do so is to take the change in concentration of reactants and products over the change in time. You'll notice that as you do the rates over time, you're going to notice between the reactants and the products, you're going to notice that they follow their stoichiometric proportions. So this is 1 to every 3 to every 2 of NH3. And so you're going to see the rates also stoichiometrically be proportioned out. Here's the data table. This data table will graph the following graph that you see on the right hand side. N2 is right here, and you'll notice that as time goes by, the amount of reactants decreases. Notice how H2 decreases a lot more sharply, and that's because it is 3 times as fast in decreasing as nitrogen. And then NH3 is going to increase over time because it's the product, and it's going to increase twice as fast compared to N2. So you'll notice the proportions all working out with the stoichiometric coefficients and proportions that you see there. And so one of the things we are going to do is calculate the rate along a time period, and that time period is between 6 minutes to 18 minutes. And so for all of these, we're going to find that basically the slope of that line. So we're going to calculate M, if you recall, is your slope. And that slope is the rise over the run. And likewise, we're also going to do it for ammonia as well. So we're going to see rates, slopes of all of those chords that you see. And that's why it defines rate as the slope of the chord. So you're going to need the data table from the page 1, the previous page, for the reaction between nitrogen and hydrogen to form ammonia. And if you look at the data table, you're looking over a span of 6 to 18 minutes. So at 18 minutes, the concentration of nitrogen is in fact 0.800 molarity. And when we take the difference, we're going to put a negative after we take that difference and then subtract. And the concentration of nitrogen at 2 minutes or 6 minutes is 2.00 molarity. And when we take the time change, which is 18 minutes going to 6 minutes, so this is our minutes, top is molarity, and that's a concentration unit that you're not too familiar with, but it's just moles over liters. So when you do your math, you get a negative of this difference that you see here is going to be a negative value, and so the negative of that negative is basically going to be positive. So in other words, your rate is never going to be a negative value, it's always going to be a positive value. And so that becomes 1.200 divided by 12 minutes. And so that final value is going to be, the rate of this is 0.100 molarity per minute. And I'm going to do the same thing with hydrogen. Take the difference in the concentration of hydrogen between 2 time points, And the concentration of hydrogen at 18 is 5.4. And once again, I'm going to do that negative, where I'm going to take the negative of 2.4 minus, or 5.4, and then I'm going to subtract the concentration of nitrogen at 6 minutes, which is 9.000. And then I'm going to take the difference between those, the difference in time. And I've already done that calculation, so I'm just going to say 12 minutes. And when I divide those two, I get an answer of 0.300 molarity per minute. Now I do the last part of the last calculation, which is the ammonia. So when I do my calculation for ammonia, the concentration of ammonia at 18 is 6.4. Minus the concentration of ammonia at 6 minutes is 4.00. Again, I'm looking at the data table from the previous page. Divided by my minutes, I will get the answer of 0.200 molarity per minute. Now, what do I notice? I notice some relationship. This is 0.1 minute, this is 0.3 minutes, and this is 0.2. You notice that that relationship really aligns with the relationships that you see in the balance equation. So this, when you ratio all the rates actually ratio to the same ratio that the stoichiometry ratios. So the rates ratio aligns with the stoichiometric ratio. From the balance equation. Now, let's go ahead and do another problem, very similar to that. It says, in the reaction A plus 2B forming 3C plus 4D, the initial rate of the concentration of B was 0.0409 molarity. And then after 15.6 minutes, the concentration of B was this amount. Units for the rate is molarity per minute. What is the average disappearance of B? So B is a reactant. We would expect it to disappear with time. A also is a reactant, so it's also disappearance. But C and D are products, and so you see that the word appearance rather than disappearance shows up. Okay, so let's go ahead and calculate A. Now, the disappearance of B, reactant B. So when we do that, we just take the difference. Once again, it's the change in the concentration, and it looks like the change in the concentration is 0.0278, and it's a negative because it's disappearing. 0.0409 divided by 15.6 minutes. And when we do the math for that, we'll get an answer of positive, and these are all positive numbers, 8.40 times 10 to the negative fourth molarity. It's a small number. Now, we're not given any data about A C, or D. We are only given data about B, the concentration of B. So how do you suppose we would go about finding A, C, or D? Well, you're correct if you said you're going to use the mole ratio, because that's exactly what will help us to proportion the other rates. So in using the mole ratio, how does A compare to B? So if you look at the equation, A is going to be half of that of B. So whatever the rate is for B, A is going to be half of that. So we're going to half B's rate. And what is half of B's rate? 4.20 times 10 to the negative fourth molarity per minute. C is going to be, and I'm going to use A as my reference here. C is going to be 3 times that in which what the rate of A is. So 3 times A. C is 3 times that of A. So if you 3 times that value, 4.20 times 10 to the negative fourth, you will get a value of 1.26 times 10 to the negative third. Punch that into your calculator and you will see that ratio relationship. And then for D, D is going to be twice that of B, so let's do twice of B. If you twice B, you get 1.68 times 10 to the negative third molarity per minute. The best way to look at this is to actually see which one is a 1 coefficient. So A is 1, and so that's why I would kind of use a multiplier of 1 times for A. So this is my 1 time, my x, 1x. And then B is, if you notice, twice, 2 times x. And then, of course, C is 3x. And then D is 4x. So you'll notice that the stoichiometry very much aligns with what you are expecting out of it, which is this is 1 time, twice, 3 times, and 4 times. So if you look at the relationship of the rates, it aligns completely with the stoichiometric proportions. Let's go ahead and graph the concentration versus time for this reaction. So it says to label the x and y axis. Our y-axis is our concentration, which is capital M, molarity, and then our time is our minutes. So let's start off with graphing A. A has it's the slowest decrease. And so I'm going to draw A anywhere here. I'm going to start off anywhere here because you actually have to start off with some reactants. So slowest decrease. And that's a pretty slow decrease. Now we go for B. B is going to be twice as fast as A. So this is your B. Now we go to C. C is going to start off at 0 at time 0 because there are no products at time 0. But then as time goes by, it's going to increase quite significantly, even more so than B. So it's going to be 3 times that of A. And then D also starts at the same point as B or C because it's a product, and it's going to increase even more so. So you're seeing an increase that's even more so. And so this is D, C, B, and A. Okay? We are going to cover the collision theory on this page. And the question that's being asked of us, a rhetorical question, is do all collisions among reactants lead to the formation of products? We describe these collisions as effective collisions. And of course, not at all. There are two factors that are required for to be an effective collision. And the two factors, firstly, the first one is that all reacting particles must have the minimum amount of energy called activation energy. Secondly, reacting particles must have proper orientation while colliding to be effective. So let's explore those two ideas. The first one is activation energy. So we're going to watch a little video that I put together about activation energy. So here's an energy diagram. It's our potential energy diagram. And we're going to be looking at two reactants, A squared, it's a diatomic molecule, B squared, another diatomic molecule. And they're reacting to form 2AB. Now we're testing to see if all collisions lead to the formation of products. So we're going to test it out with low kinetic energy. So these particles are going to have low kinetic energy to start. And then we're going to test another scenario where they're high kinetic energy. So let's see what happens in low kinetic energy. So we're starting at the reactants on the energy diagram. Now, upon seeing them collide, you'll see them collide very slowly because they have low kinetic energy. And the particles bounce right off each other unchanged, which means the particles do not form, that collision did not form products. So it's an ineffective collision. Now, you notice that those reacting particles were moving up in potential energy, but they couldn't get over the activation energy. So there wasn't enough activation energy to form an effective collision. Now let's see what happens in the second scenario. High kinetic energy. Those particles are moving much faster, and we did overcome the activation barrier, which is called the activation energy, leading to the formation of products in this case. And you'll notice change particles. Now you have two AB particles. So the reaction or the collision there was effective in the end. At this point, I'd like you to summarize what you observed in that video with a potential energy diagram for when I clicked on the high kinetic energy reactants or the low kinetic energy reactants. Go ahead and summarize it in this area. Now, aside from particles having enough activation energy, particles also have to have proper orientation. So it's necessary for them to have effective collisions. So here's a reaction, generic reaction. We're going to look at two possible collisions. You'll notice that the first collision is a side-to-side collision, and you'll notice that you're forming your end product, which is AB. It enables this two ABs to be formed as a product. You'll notice now, instead of the parallel collisions or the parallel collision, now you're seeing a perpendicular between the particles. So one's lined up this way and the other one's lined up vertically. So horizontal and vertical bounce against each other, and this is an improper collision because you'll notice that the formation of the products is not a doable thing. You're not enabling this activated complex to become products easily, which is your two ABs. So this is why this is an ineffective collision in the end. Now, chemical reactions need to meet both the activation energy and the proper orientation according to the collision to be effective collisions according to the collision theory. In what ways can we encourage the increase of activation energy and proper orientation? There are 5 of them, and we're going to talk about the 5 ways we can encourage. We can actually manipulate concentration. We can pick reactants that are more reactive. We can manipulate temperature, add a catalyst, change the surface area of our reactants. So let's go ahead and go to the next page to explore these 5 ways we can speed up a reaction. So these are 5 factors that can increase the reaction rates. The first one we're going to talk about is up here. its concentration. And I put a graph, the same graph that we started off this unit with, to show that if I add more reactants, N2 or H2 and N2, you're going to see that the reaction occurs a lot quicker because there are more to basically bounce off of each other, and thus leaving greater chances of having effective collisions. So a higher concentration leads to a more reactive or a faster reaction. Temperature, we saw that earlier in this diagram right here, where if I increase kinetic energy of reacting particles, which means I'm increasing the temperature of the system, I'm actually going to see the reaction overcome that activation barrier or the activation energy and form products in the end. Then we go to surface area. So I have a little fire, a startup fire. So inside are kindling versus the fire log on the outside. So which one burns faster? Well, if you said the kindlings first burns faster, you're right, because that's what you usually use to start up a campfire, kindlings, because they burn quicker and they start up that fire to then burn the firewood afterwards. So surface area definitely increases. The more surface area, the faster the reaction. Catalysts. So what a catalyst does is a catalyst actually lowers the activation barrier or activation energy. And so I'm going to draw in what a catalyst does to this endothermic energy diagram. So it actually causes the reaction, the hill that you climb right here, to lower. So this is what an added catalyst does to this reaction. It lowers the activation energy, and it enables for the reaction to occur much faster if I can get to the products quickly. So I can go over this hill much more faster if with that lowered activation energy.
And how a catalyst is able to lower the activation energy of a chemical reaction. And so the catalyst that you see right here is platinum. It's a piece of metal, and it's a solid piece of metal that is a surface for which your reactants are going to be drawn to, and that will then lower the activation energy for the reacting particles that would be needed in order to overcome and become products. So I'm going to play this out, and you're going to notice exactly what I just mentioned, how the reacting particles A squared and B squared are going to be attracted to this platinum catalyst, and that's what's going to lower the activation energy. So A squared is drawn to platinum. And notice how A squared and B squared are not colliding with the same kind of energy that's needed to get through the activation barrier. It's because now we have platinum as a surface to draw those particles together. So that's how we're lowering the activation energy.
And so now the last factor that will increase the rate of reaction is something that you can only control to some degree, and that is the reactivity reactance. So you can substitute certain reactants in for a reaction that will speed up the reactions, and that's why I say that you can only control that so much. And the one that we're going to look at is the alkali metals. So this whole group is made up of elements that have one valence electron. So this shows for one valence electron. And that one valence electron is easily lost. So you want to, you can lose that valence electron easily. Now, as you see, as you go from the top of the periodic to the bottom, from lithium to rubidium, you'll notice an increase in reactivity. And that's because the valence electrons are further away from the nucleus. So there's a weaker core charge as a result. So there's greater energy levels. Rubidium is larger than lithium, which is smaller, and that's why rubidium can lose its one valence electron a lot easily compared to lithium. And so when you switch out rubidium for lithium, you'll see that rubidium's reaction is going to be a lot more, is going to be faster than lithium. Now take a couple of minutes and pause the video and read on equilibrium, because equilibrium begins this idea that rates of the forward reaction equals the rate of the reverse, and that's why we're talking about rates in this unit as well, because equilibrium is defined by average rates being equal of the forward reaction and the reverse reaction. So let's compare what we're familiar with, which is a reaction that goes to completion, where you're dealing with a limiting reactant, and oftentimes you're going to see a one-directional arrow. And in a reaction that goes to completion, you're going to see A react to form 2B, but until 2B, the formation of 2B stops when A runs out. So if you look at this, A is decreasing, and then it decreases until it hits a concentration of 0 as time passes. And that is when B also levels out and no longer increases. But notice how B is twice the rate of A in the end, just like the stoichiometry shows. We're going to see what happens in a reaction that is reversible, where you reach equilibrium, and of course to denote that we see a double arrow. So this is your equilibrium situation. And in that case, you're going to see A decrease with time and levels out. B is also going to increase twice as fast and also level out. And the leveling out between A and B is what we call equilibrium. So equilibrium occurs where they remain constant. The concentration remains constant over time. So I would call this the equilibrium point right here, where I see them maintaining to be constant over time. And so this part right here is where we've been studying. It's the kinetics part, where you're seeing changes in concentration over time. Equilibrium is what will happen eventually to any reversible reaction. So read this little story, the equilibrium story, fill in the blank, but also we're going to graph what we see here. So we're going to graph this equation between nitrogen and hydrogen, and we're going to sketch it according to what we see. So you'll notice in graph A, the reactants and products are not equal at equilibrium. So equilibrium occurs at this dotted line right here, and you'll notice how the concentrations are constant over time, unchanged over time, and so this is where equilibrium begins. Now notice how they are not lined up or crisscross each other in any way. So equilibrium is not defined right here where they crisscross each other. It's defined when their concentrations are constant over time, and they don't have to be equal. They are not necessarily equal. Sometimes they can be, but that's not what defines equilibrium. All right, let's get into the equilibrium expression. So now that concentrations of reactants and products remain constant over time at equilibrium, we can actually, the fact that they're constant allows us to ratio the products over the reactants, raise them to their stoichiometric coefficients, and have a constant called the equilibrium expression and constant. Now, reminder, the little bracket is actually representing molar concentration, which is capital M, molarity. If you look at this general equation, you're seeing that in this generic reaction, you always take the products, which is C and D, concentration, and raise them to their stoichiometric coefficients, y and z, divided by, there's a division right here, so make it very clear that it's a division that we should see. So this is divide. So this is divided by the reactants, which is A and B, raised to their stoichiometric coefficients. Make it really clear. K is, because these reactants and products are constant over time, we can ratio K, and we can understand a lot about K from that. For instance, if K is greater than 1, that means at equilibrium, there's more products than reactants. That's why a ratio can be a ratio where it's greater than 1. That's why it's high KEQ, greater than 1. Now, if it's equal to 1, that means neither reactants nor products are favored. So both reactants and products, same number, and so it ends up being 1 in the end. Now, if the equilibrium is less than 1, that means that the reactants are favored. So it's favoring the left side, and that means more reactants than products. More reactants, which gives you a ratio that is less than 1, a lower number in the end. So let's go ahead and write the expression. So we're going to practice writing the expression, and then we're going to calculate KEQ constant as well. The expression is always products over reactants. So if you look in here, recall that the products that are solids and liquids do not count in the equilibrium because their concentration doesn't change much. So we treat them as though their concentration is 1 molarity. So we know that anytime we multiply or divide by 1, you always get the same number. So these two are your products. This is your product side. This is your reactant side. So we're going to do products over reactants. So I have to denote concentration, which is in brackets. So we start off with the products. So the product that counts would only be CaF2, so calcium fluoride. Water is a pure liquid. Pure liquids do not affect equilibrium. So the only product to count in this equilibrium expression is going to be calcium fluoride. And then we look at the reactants. This is a solid, so solids are not to count. And so the only one that we count is going to be the HF. So I'm going to actually mark off what we don't count. So this one we don't count, and this one we don't count in the end.
So the question is, why do solids not affect equilibrium? So right now, the system that you see in here, in this vessel, is at equilibrium. And you know it because you see that the 5 gas particles, or carbon dioxide molecules that you see floating around, stays at 5 over time. So in other words, it's 5 right now. 10 seconds later, it's still 5. So it's actually staying constant. The concentration of that carbon dioxide is staying constant over time. Now, you also notice some calcium oxide as well as calcium carbonate. That's in green. Calcium oxide is in orange. When I add, and by the way, this system's at equilibrium, and aside from the concentration, there's an error on this. There should be a double-headed arrow. So imagine the arrow going the other way as well, the reverse direction. As I add more calcium oxide, watch to see what happens. Does that change the amount of carbon dioxide? It's still 5, right? So it looks like adding more solid to a system that's at equilibrium has no impact on it. So if I add more or take away, you're going to see that it's not going to impact. Likewise, for calcium carbonate, which is also a solid, so these two are solids, you're going to see that it has no impact on the system. And you would see impact if you saw amounts of carbon dioxide changing. Adding more did not do anything. Notice adding more calcium carbonate didn't change the amount of carbon dioxide. So hopefully the takeaway is knowing that solids added to a system at equilibrium is not going to impact that impact that equilibrium system.
Now go ahead and finish the rest of these problems, making sure you do products over reactants and eliminate the pure liquids or pure solids and pure liquids. So make sure you eliminate them from the equilibrium expression. The answer key is right here so you can check your work as you go through it. So now we're going to calculate the K constant in this example problem. Here's our data chart with equilibrium concentrations of each of our substances in our reaction, and we're given those concentrations right here. Because we have equilibrium concentrations, we can substitute it into our equilibrium expression, and then we can calculate our KEQ constant from that. So let's write the expression first. Again, it's products over reactants raised to their stoichiometric coefficient. So looking at the reaction, all three of these substances, CO, CH4, and H2O, all have a coefficient of 1. Products are CH4 and H2O. So you write both of them raised to their first power because the stoichiometric coefficient is 1. And then of course the products or the reactants is CO and H2 raised to their corresponding stoichiometric coefficient. Notice H2 is 3 raised to the third power, just like it is in the equation. So now we can substitute those equilibrium concentrations depending on which experimental number we're asked to calculate it for. B is asking us to calculate experiment 1, so we substitute all those values and do the math and raise them to their corresponding stoichiometric coefficient, and we see it's 3.933. The same thing with experiment 2, and we notice that both experiment 1 and 2, when we substitute their equilibrium concentrations in to the expression, we see that the value is the same, which tells us that any experiment or wherever you reach equilibrium for the same reaction, as long as you're at the same temperature, is going to give you the same constant. And that same constant is what allows us to be able to use this equilibrium constant to calculate and understand equilibrium much more. Based on the equilibrium constant for experiment 1 and 2, is the reactant, product, or neither favored at equilibrium? So it looks like because our constant is greater than 1, it looks like we have more products than reactants. So we have this scenario for our KEQ to be greater than 1, which means there's more products, greater number of products than reactants at equilibrium. Okay, so pause the video. We're going to get into some stresses to a system that's at equilibrium. So we're going to understand, according to Le Chatier's principle, what happens. So pause, read, fill in the blanks for all the major ideas that I'd like you to focus on in Le Chatier's principle. Continue reading on the top over here, and it continues from the prior page, and we're going to get into Le Chatier's principle and some stresses. And again, just a reminder that stresses are bad. You want to undo those stresses. So everything I'm going to talk about is going to be whatever the stress is, I'm going to do the opposite to undo that stress. So the equilibrium system is going to find a way to compensate for that stress. So let's go ahead and begin. The first stress is a stress on concentration. And so when you increase amounts of reactants or products for a system that is already at equilibrium, you're going to impact it in different ways. Let's see what specific stress will cause the reaction to either shift forward, shift reverse, or have no change. No change means there's no impact on the equilibrium system. So let's begin. If I add more N2, Now N2 is on the reactant side of the equilibrium reaction. So adding more N2 would say, okay, we got to get rid of it. How do we get rid of N2? Well, we go forward, in the forward direction, very fast compared to the reverse. So the forward reaction is going really quickly, while the reverse is slower than the forward. And that will then get it back to equilibrium. And so, in other words, you are going to shift forward, as I stated, when you add N2. What would happen if you add N or O2? The same thing that happened when you added N2 will happen when you add O2, because it's on the same side of the it's on the same side, which is the reactant side. So you're going to see it find a way to try to consume that O2. How do you consume it? You go very fast forward. So you're going to be reacting these guys really quickly to form your products. And again, so it's going to be a forward shift until it reaches equilibrium again. What happens if you add NO2, which is the third separate scenario? So if you add NO2, so you're adding now the product, upon doing so, the reaction is going to want to reverse itself to go fast in the reverse direction to try to get rid of NO2. And to do so is to reverse it until it reaches equilibrium again. Every scenario is trying to get back to the equilibrium state. Now we look at the next stress. The next stress is an effect on pressure or volume. Remember that pressure and volume are inversely related. So if I increase the volume, it decreases the pressure. Vice versa. Okay? So noticing the inverse relationship between pressure and volume. In the first scenario, there's two types of scenarios. One where there's actually unequal number of moles of gases. Now, what exerts pressure? Gases. And so because gases exert pressure, you have to count the moles of gases on the reactant side, and there's 4 total moles of gases on the reactant side and 2 moles of gases on the product side. So when you decrease volume, which means you're increasing pressure, now you've left less room. Now, if there's less room, what side do you think is going to favor? It's going to favor less moles of gases. So you're going to try to combine more moles of gases so that you can make less moles of gases. And to do so is to shift in the forward direction. The opposite would be the reverse direction. So if you've got more room now, volume-wise, so there's more volume, thus less pressure, you're going to try to make more pressure. How do you make more pressure? You are going to, or make more moles of gases. Then you're going to shift to the reverse direction. What happens if they're equal? The moles of reactants and products are equal. And let's make sure we count that to see if they're equal. So here we have 2 moles of gases. And then here you see 2 moles of gases. So they are definitely, the moles of gases on the reactant side and product sides are equal. So with that, there's going to be no change. The reaction is not going to go faster in the forward direction, nor is it going to go faster in the reverse direction to compensate for the stress. So there's no change. Now we look at stresses on temperature. When there's a stress on temperature, what you're going to do is you're going to have to know whether the reaction is endothermic or exothermic. So once again, we're going to really stress the use of that triangle, and that triangle is going to represent our heat. So this triangle is a symbol for heat. And let's look at the first scenario. In the first scenario, your change in enthalpy is actually negative. So that negative means the reaction is exothermic, which means our heat is going to be positioned on the product side. And so if I increase temperature as this specific stress states, I am going to find a way to try to absorb that energy, the heat. And the absorption is this way. In other words, it's exothermic going this way, left to right, but then endothermic going right to left. So you're going to try to absorb that heat. And absorb means endothermic, which is the reverse. So the reaction is going to reverse to try to compensate and basically decrease the temperature. So it's absorbing that heat. If you have a decrease in temperature, well, what do you think the reaction is going to want to do? Of course, it's going to want to make heat. And to make heat means go to the exothermic direction, which is the forward direction. And that will make more heat to try to reach equilibrium again. What happens in the next scenario where you have an endothermic reaction? Once again, delta change in enthalpy is positive, so it is endothermic. And so we're going to put the triangle on the reactant side, anywhere on the reactant side. If you increase in temperature as the stress states here, you're going to want to absorb that heat. And so it's going to go endothermic, which means it's the forward direction. The reaction is going to move forward to try to reach equilibrium. And of course, the reverse, opposite. And so the last one is the catalyst. Adding a catalyst actually speeds the forward in the same manner as the reverse, so it's not going to affect the equilibrium in any particular way. So adding a catalyst has no change on the equilibrium. It might speed up the reaction, both the forward and the reverse, but it does not change or shift the equilibrium in any way. So let's look at some examples. All these are examples to practice. If you'd like to practice on your own, pause it and you can try it on your own, and then you can check with me as I talk through the answers. Okay. The first one, removing COCl2. So you're taking away this amount for the system that's at equilibrium. So notice the double arrow. So you're going to want to make more, right? Removing means you want to make more. How do you make more? Well, you shift forward to try to make more COCl2. That will increase the rate. So this is going to be a forward shift. B, you increase temperature. So if there's a temperature change, I'm always thinking I have to see if it's endothermic or exothermic. And it looks like it's exothermic because of the negative. The negative means we're dealing with an exothermic reaction. Now, what would happen if I increase the temperature? If I increase the temperature, I want to go and absorb that temperature. So it's going to go in the endothermic direction, which is the reverse direction. So endothermic is absorbing heat this way. So you're going this way. Whereas exothermic is going from left to right and you're releasing heat. I don't want to further release heat because that's going to stress the system out further. So I'm going to absorb that heat, and that is the reverse shift. A decrease in volume means an increase in pressure, just always that inverse relationship. So I'm going to have to count my moles of gases. Anytime when I'm dealing with pressure, I would like to make sure I count my moles of gases. I see 1 mole of gas on the product, and I see 4 moles of gases on the reactant side. So if I increase pressure by decreasing volume, as stated right here, increase pressure by decreasing volume, I'm going to want to move to the side with less moles of gases because I have less room. And I've created more pressure. So if I move towards the reactant side, I'm creating more pressure because there's more moles of gases. So I'm going to move towards the products, which means I'm going to shift right, which means in the forward direction. I'm going to move in the forward direction where there's less moles of gases. For the next one, you're adding PBS. Now, of course, you're going to jump over and see that PBS is right here. And I know you're probably not noticing this, but you need to notice this. PBS is a solid. And what do we say about solids and their impact on equilibrium? They have none. So because this is a solid, you're going to see no change because solids have no impact on the system that's at equilibrium. I'd like to add this video on how pressure and volume changes systems that are at equilibrium.
So this reaction is at equilibrium, and technically there should be a double-headed arrow right here, so there's a little bit of an error. If you count how many particles there are in this container, gas particles that is, you'll see 6 nitrogen dioxide molecules roaming about, and there should be 2 dinitrogen tetroxide molecules roaming about. So count it and you can see it from the modeling. I'm about to compress this container. When I compress this container, we're going to see less volume, less room for these particles to move. And so their equilibrium will find a way to shift in order to compensate for the less room that you have. And so let's look to see what the shift is. You'll notice that there are now more dinitrogen tetroxide. There's 2 more. And of course, there's 4 more is lost of the nitrogen dioxide. So there were 6 initially. 4 of them were taken away to make two of the dinitrogen tetroxide. And why that happens is because there's less room. Where there's less room, the equilibrium reaction is going to move towards the side with the less moles of gases, which is dinitrogen tetroxide. So for every 2 particle, you're going to be forming 1, and it's going to move quickly to form 1 so that it can compensate for the less room that you have inside this container. If I expand, you'll notice that the particles will go back to where it originally was, which is 6 particles of nitrogen dioxide and 2 particles of nitrogen tetroxide. When I compress, once again, you'll see the particles, 4 of the nitrogen dioxide decreasing to make 2 of the dinitrogen tetroxide. And we are reestablishing equilibrium, and how we know is as time passes, you'll see that the particles the amount of reactants and products remain constant over time. So let's go ahead and look at another different scenario, so another reaction. In the second reaction, you're going to see, once again, the error is the arrow, you're going to see 2 moles of you'll see the reactants, which is the yellow ones are the hydrogen, diatomic molecule. Purple are the iodines. And there's 2 hydrogens and 2 iodines. And of course, you also see some products, which is the Hi particle, gas particle. And there's it looks like there's 2 of them. So notice 2 of everything, 2 hydrogen, 2 iodine, and 2 hydrogen iodide particles as gases. Now I'm going to compress, and when I compress, you're going to see if there's any changes in the amounts of both hydrogen iodine and hydrogen iodide. So let's count. You see 2 hydrogen molecules, you still see 2 iodine molecules, and you still see 2 hydrogen iodide. Now, upon compressing, what you've done is you've changed the volume. Thus, you increase the pressure inside the system. But because there's 2 moles of gases on the reactant side and 2 moles of gases on the product side, you're not going to see this reaction try to compensate or the shift occur according to Le Chatelier, because they have the same number of moles of gas particles. So the reaction doesn't know where to go to try to compensate for equilibrium. So it looks like this whole reaction, this whole system is going to increase in pressure one way or another, and the reaction can't compensate for or will not shift forward nor reverse in order to try to reach equilibrium again.
So all of this is continued practice on the Shakyas Principle. Finishing up, I'm going to continue, I'm going to go a little faster. So this is an endothermic reaction, letter E, and endothermic because I see that delta H is positive, and so I know heat is on the reactant side. I'm going to squeeze it into this side here. If I increase temperature, I'm going to see that I'm going to shift to the side away from heat or endothermic. So it's actually forward. Forward is my endothermic direction, away from heat. I go to F. In F, I'm increasing pressure, which means it's another way of saying I'm decreasing volume. So if I'm looking at volume and pressure, I'm adding moles of gases on the reactant side and the product side. I have 2 moles of gases here, and then I have 1 mole of gas on the product side. And an increase in pressure means I want to decrease the moles of gases. So I'm going to shift forward to try to decrease the pressure by going towards less moles of gases. For the next one, the same thing. So I'm going to count moles of gases, and it looks like I have 5 moles of gas here. Again, I have to look at the states of matter to make sure I see it. And I have 6 moles of gases here. So, and it looks like I'm decreasing pressure, so I want to try to increase pressure by moving forward towards the more moles of gases. Adding a catalyst, like we stated earlier, has no effect, so no change on the system that's at equilibrium. Once again, on example 2, we're seeing the same kind of problem, all le Chatier, heat on the reactant side because the enthalpy is positive. Change in enthalpy is positive. We're going to see all of these different changes that you see here. So the first one is a decrease in volume or increase in pressure. What would happen as a result? It looks like it's going to shift towards the side with less moles of gases. So I'm going to have to count my moles of gases. Once again, I see 2 moles of gases on the product side, and then I see 0 moles of gases on the reactant side. So in order to decrease pressure, I'm going to move towards the this direction, the reverse. Now, when it says right here, the effect on the quantity, what that means is if as a result of shifting this way, which means it's going faster towards the reactants, I am the quantity of NH3 is decreasing quite significantly. And so the effect is for NH3 is it's decreasing if it's shifting left. Decrease in temperature, I wanted to try to find a way to increase the heat, so I am going to go towards the exothermic direction, which is the left, towards heat, making more heat. And what it does to the amount of ammonium chloride, which is on that same side, so ammonium chloride is where heat is, and so it's going to increase my ammonia amount. Adding more NH3, in order to undo that change, I'm going to have to remove NH3. So the only way to remove NH3 is to shift it towards the left. So I'm shifting it this way towards the left. And that will have an impact on the amount of hydrogen chloride by decreasing it. So it's actually going to decrease the hydrogen chloride because it's going to be shifting towards making more ammonium chloride solid. Now removing ammonium chloride. Once again, I'm always going to notice to see what state of matter it's a solid, so there's going to be no change no change. If there's no change in that system, you're going to see the amount, the quantity for HCl compared to original is not going to be there's no change as well, because the reaction's not favoring or not going faster the forward or nor reverse. Removing HCl. If I remove HCl, removing this, I want to make more of it because I want to undo this change, this stress. So how do I make more? Well, I go towards it. So it would be moving towards this way. And in doing so, because ammonium chloride is in the reactant side here, we're going to see that the amount of ammonium chloride is going to decrease with time as I move away. So it's decreasing to form these two substances quickly until it reaches equilibrium again. All right, for the third question, it's asking us how will the K constant change with each stress on the following reaction. So we're looking what changes K. And honestly, the only thing that changes K are things that are temperature related. So there's going to be no change for this one. No change here. And I'm going to abbreviate it NC, 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 and NC. The only thing that changes is temperature. So KEQ is temperature dependent. And because it's temperature dependent, that's the only thing that will change. So in order to know how KEQ will change is to understand whether it's an endothermic or exothermic. And from the looks of it, it looks like it's an exothermic in the forward direction because I see heat right here. So an increase in temperature. If you increase temperature, according to Le Chatelier, you're going to try to absorb that heat, which means the reaction is going to shift reverse. If you're shifting reverse, according to the KEQ, which is products over reactants, if you're shifting reverse, that means you're making more. If you're shifting this way, you're making more reactants. So you're making more reactants, and of course you're losing products. So what is this ratio going to look like as a result of this? So you're going to divide it into a larger number, and of course there's less to divide, so it's going to be even a bigger KEQ. So KEQ is actually going to be increasing in the end. So the key is that the reactants are increasing, and of course products are decreasing as a result. And there's much more reactants than products.